Hi guys, this is Nick Fitzke, and I'm a professor in the chemistry department. Welcome to the Mississippi State University NMR facility. In this video, I'm going to introduce you to these instruments and discuss how fortunate MSU is to have a facility like this. Hopefully I'll convince you that these systems are a valuable part of our chemical toolbox. Finally, we'll talk about some exciting changes that are going to be happening in the facility this year. First though, we got to talk about safety. Right now, you're standing among several very powerful magnets. You should be perfectly safe if you stay behind the yellow cordons, but please observe those limits. Also, because we can never perfectly predict how critical electronics are going to respond, if you have a pacemaker, a glucose pump, or some other electronic implant, please stand by the door. The safe line for these devices is actually very close to the magnets themselves, but we want to be extra careful. Now, with that out of the way, you're going to be doing a lot of chemistry experiments in Gen Chem this semester. Those experiments are designed to support your learning of basic chemistry. Some of the topics will be super interesting to you. Others might take a little while to appreciate. As you tour the NMR facility, I want you to see where your chemical training can lead you. The principles you learn this semester may be tedious at times, but they form the foundation for how these really interesting instruments work. As you continue in chemistry, you'll learn how to use tools like this to collect data. That data can help you answer questions. Anything from, what poison was used in this homicide? To, how stable is this new pesticide I made? To, why did the drug I just make have side effects? You don't have to be a pure chemist to answer questions like these, but knowing chemistry can help. And tools like NMR provide one way to answer questions which can ultimately lead to a great career. Anyway, enough about jobs, let's get back to basics. NMR stands for Nuclear Magnetic Resonance. With one exception, the instruments you see around you are designed to detect the behavior of atomic nuclei. Remember that atoms have nuclei surrounded by electrons, and electrons can participate in bonding, forming molecules. Molecules are formed by two or more atoms bonded together. And certain atoms, for example hydrogen atoms, respond to radio frequencies. That response will change depending on how the bonds around that atom are structured. Now to detect this, we need big magnets, and that's what you're seeing around you right now. The white cylinders you see are large containers of liquid nitrogen at minus 320 degrees Fahrenheit. Inside those cylinders is a smaller cylinder of liquid helium, and that's even colder, a whopping minus 452 degrees Fahrenheit. At the core of the cylinder, however, is the key component: miles and miles of carefully wound superconducting wire. The helium keeps the wire cold, and once a current starts going in the wire, it can continue without any additional power, and that can last for years, even decades. Incidentally, some of you might have heard the excitement about a new potential room temperature superconductor, LK99. Right now it doesn't look like that material is going to pan out. But one of the reasons it's exciting is that superconductors, and especially liquid helium, are expensive. A room temperature superconductor would dramatically change what's possible in a facility like ours. So what can you do with NMR? Remember, NMR detects signals from individual atoms, and those atoms differ based on the structure of the molecules. One application is the analysis of complex chemical mixtures. Here, you're looking at NMR spectra from two different blood samples from cows, collected right here at MSU. The top spectrum shows blood from a healthy cow, and the bottom spectrum is a cow with a respiratory infection. By comparing these two different spectra, we can develop diagnostic tools to identify sick cows, or sick people, earlier. NMR can also help to determine the three-dimensional structure of molecules. You're right now looking at a bacterial protein called autolysin R2AB. This protein allows bacteria to attach to surfaces, like infections on medical implants. Many of you will learn about proteins later, But for now, just think of them as complex three-dimensional molecules. Just using NMR, we determined the 3D arrangement of those atoms in this protein. Remember, each atom has its own signal that depends on its electronic environment, and using that information, we can determine how atoms in a complex molecule fit together. Around you, you'll see 3 different magnets: small, medium, and large. We talk about these magnets using the strength of the magnetic field, which is related to the frequency of radio waves that we use to excite the atoms. The smallest magnet we have is 300 megahertz, the mid-sized magnet is 500 megahertz, and the largest magnet is 600 megahertz. Larger field strength allows us to detect signals that are weaker, and it also improves the resolution. On the 600 NMR, we can distinguish signals that are closer together than we can on the 300 NMR. Stronger magnets also let us look at larger biological molecules. But each system you see here is optimized for its own role. While the 600 is our most sensitive magnet, the 500 is great for high throughput because of its sample changer, and the 300 is set up to detect a broader range of atoms. NMR is related to MRI imaging. The magnetic resonance is the same. And if you have a sample that would fit in one of these little tubes, we could do that right here in the facility, although that might not be so practical. Some of you might have noticed that one of these instruments is not like the others. This is the EPR system, and EPR stands for electron paramagnetic resonance. The principles are similar to NMR, but instead of looking at nuclei, EPR detects unpaired electrons. Using EPR, you can look at the bonding environment of metal atoms, which form the functional core in manufacturing plastics and other materials. And metals are crucial for you and me to survive. Just think of the iron that carries oxygen in red blood cells. EPR is a great complement to the NMR instrumentation that we already have. In the coming year, we're going to see some big changes in our facility. First, you might already notice the helium manifolds on the wall. We're going to start collecting and recycling all of our helium. Remember, we need helium to keep the superconductors cool, and over time, that helium boils off. Helium is so light that it can escape the Earth's gravity, so it's becoming increasingly expensive. Helium has more than doubled in cost over the past 2 years. Recycling not only saves our facility money, but it ensures that we can be around for future bulldogs. The other big change is that we're getting a new $2.5 million NMR with a magnetic field strength of 800 megahertz. That's more than 350,000 times the strength of the magnetic field you and I experience here on Earth. The stronger magnet allows us to study even more complex systems with greater sensitivity. Look for that to be installed soon. If you're doing undergraduate research as a chemistry major, or as you continue to take chemistry classes, you'll be able to access this instrumentation and use it firsthand. We chemists might be a little nerdy, but we pride ourselves on training our students and giving them the opportunity to use the same cool stuff that we use. Remember, you've got to walk before you can fly. And as new chemists, you're still learning the ropes. But I promise you, all the topics you cover in general chemistry translate to how this equipment works in the real world. Stick with it, and pretty soon you'll be developing and characterizing materials in your future jobs. Thanks for visiting the NMR facility today. I wish you great success in your chemistry classes, and I encourage you to talk to the chemistry professors about the tools that we work with every day. At the end of this video, I've included some contact information for faculty who use this facility. We hope to hear from you soon, and, as always, Hail State!